Good day, everyone. We are the Group 2 from Grade 11 Bernoulli, and this is our presentation for Week 2, Integration by Substitution.
Integration by substitution, also called U substitution or the reverse chain rule. In this method, any given interval is transformed into a simple form of integral by substituting the independent variable with the others. It is the counterpart of the chain rule for differentiation and can loosely be thought as using the chain rule backwards.
The first example, integrate 2dx. So in this example, we will apply the rule of integral constant where a dx is equals to ax. Then we will have 2x, then add the constant c. So the answer is 2x plus c. Example, we have integrate x raised to 5 dx. First, we will let u is equals to x and du is equals to dx. Then substitute and integrate. We now have u to the power of 6 all over 6. Then substitute and the answer is x raised to 6 over 6 plus c. Third example, we have integrate 5x cubed dx. Here we will let u is equals to x and du is equals to dx. Substitute, we will now have integrate 5u cubed du, separate 5, then integrate, we will have 5 times u to the fourth all over 4, simplify and then substitute, and then the answer will be 5x to the fourth all over 4 plus c.
For our fourth example, we have integrate 5x raised to 9 plus 6x raised to 5 times dx. Here, we let u be x and du be dx. Substitute this and integrate, we'll have 5 times u raised to 10 over 10 times du plus 6 times u raised to 6 over 6 times du. Simplify, the answer is 1/2 x raised to 10 plus x raised to 6 plus c. For the fifth example, we have integrate x raised to 6 times e raised to x raised to 7 plus 1 times dx. Here we'll let u be x raised to 7 plus 1, du dx is equals to 7x raised to 6, du is equals to 7x raised to 6 times dx, and dx will be equal to du over 7x raised to 6. We can cancel x raised to 6 and separate 1 over 7. It will be 1 over 7 times e raised to u times du. Substitute u, the answer will be 1 over 7 times e raised to x raised to 7 plus 1 plus c. The sixth example is integrate 10 raised to 4x times dx. Here we'll let u be 4x, du will be equal to 4 dx, and dx is equals to 1/4 du. Substitute, we'll have 10 raised to 4 times 1/4 du. We can separate 1/4 and it will be 1/4 times 10 raised to u du. The integral of 10 raised to u with respect to u is 1/4 times 10 raised to u over ln times 10 plus c. Simplify, we'll have 1 over 4 times ln times 10 raised to u plus c. Replace u with 4x. Our answer is 1 over 4 times ln times 10 raised to 4x plus c.
For our seventh example, we are given an equation which is the integral of 2x plus 3 raised to negative 1 dx. And our first step there is to apply the rule of exponent, which will give us the integral of 1 over 2x plus 3 dx. And by using the u substitution, we're going to substitute 2x plus 3 with u, and we're going to get the du, which is 2 dx. But in order to get the same value with the equation, we're going to use 1/2 du is equal to dx. Then we substitute it to the equation, which will give us the integral of 1 over 2u du. And we take out the constant, which will give us 1/2 times the integral of 1 over u du. And by using the table of integrals, we're going to get the 1/2 natural logarithm of the absolute value of u. And by taking back 2x plus 3 as u, we're gonna get 1/2 natural logarithm of the absolute value of 2x plus 3, and we add a constant there, which is plus c. So our final answer is going to be 1/2 natural logarithm of the absolute value of 2x plus 3 plus c. Now for our 8th example, we are given an equation of the integral of sine 3x dx. And the first step is to use the u substitution by substituting 3x with u. And we are going to get the dx of 3dx, but in order to get the same value in the equation, we're going to use 1/3 du is equal to dx. And by applying it, we're going to get the integral of sine u times the 1/3 of du. And by picking up the constant, we're going to get 1/3 times the integral of sine u du. And by using the table of integrals, we're going to get the 1/3 times the negative cosine of u. And then by substituting back u to 3x, we're going to get 1/3 times the negative cosine of 3x. After simplifying it, we're going to get negative 1/3 cosine of 3x. And we're going to add a constant to the solution, which will give us our final answer of negative 1/3 times the cosine of 3x plus c. And for our 9th example, we are given an equation which is the integral of cosine 5x plus 1 dx. And our first step there is to do the u substitution by substituting 5x plus 1 with u. And we're going to get the value of du, which will give us 5 dx. But in order to get the same value as in the equation, we're going to divide both sides by 5, which will give us 1/5 du is equal to dx. And then after substituting it, we're going to get the integral of cosine u times the 1/5 du. And then after taking out the constant, we're going to get 1/5 times the integral of cosine u du. After using the table of integrals, we're going to get the value of 1/5 sine u. And after substituting 5x plus 1 with u, we're going to get 1/5 sine 5x plus 1. After adding a constant to the solution, we're going to get 1/5 sine of 5x plus 1 plus c.
Okay, so now I will be discussing these next 3 problems. Our given is the integral 1/2 cosecant to the second power x dx. Our first step is to rewrite the given as cosecant squared x over 2, so that the process will be easier. After that, linearity would be applied, and then solving the integral of cosecant squared x dx will give us negative cotangent x. The next step involves substitution. Our final answer will then be negative cotangent x over 2 plus c. The second problem, 1/2 cotangent squared x dx, doesn't differ much from the first one. So after rewriting the problem as cotangent squared x over 2, the next step will involve the application of linearity, giving us 1/2 of integral cotangent to the power of 2 x dx. And then we need to simplify the integral cotangent squared dx by using trigonometric identities, giving us cosecant squared x minus 1 dx, and then apply linearity again. After that, we need to simplify both the integral of cosecant squared x dx and the integral of 1 dx. By doing so, we will get negative cotangent x and x with the application of the constant rule. Now, putting everything in place will give us the final answer of cotangent x plus x over 2 plus c. The equation given for this next problem is the integral of cosine squared x secant x. We will get the integral of cosine x if we simplify the given, resulting to sine x. Our final answer will then be sine x plus c.
Number 13. The integral of cosecant squared x times cotangent x times dx. We first let u equals cosecant x, and du is the differential of u with respect to x, which is negative cotangent x times cosecant x times dx. And negative du equals cotangent x times cosecant x times dx. Then we can substitute the variables to the integral, and we will get the integral of negative u times du. And since negative 1 is constant, we can move negative 1 out of the integral. Negative 1 times the integral of u times du. Then integrate the integral and multiply it by negative 1. We will get negative 1/2 u squared plus c. Then we can now substitute the cosecant x to the u. Negative 1/2 times cosecant squared x plus c. Number 14. The integral of 2 tangent x times dx. Since tangent x is equal to sine x over cosine x, we can substitute it to the tangent x. The integral of 2 times sine x over cosine x times dx. And we can let u equals cosine x and du is equal to negative sine x. So negative du equals sine x. Then we can substitute u and du to the integral. The integral of negative 2 over u times du. And since negative 2 is constant, we can move negative 2 out of the integral. Negative 2 times the integral of 1 over u times du. Then integrate the integral and multiply by negative 2. Negative 2 times ln times the absolute value of u plus c. Then we can now substitute cosine x to u. Negative 2 times ln times the absolute value of cosine x plus c. Number 15. The integral of 2 times cotangent x times dx. Since cotangent x is equal to cosine x over sine x, we can substitute it to the cotangent x. The integral of 2 times cosine x over sine x times dx. Then we can let u equals sine x and du equals cosine x. Then substitute u and du to the integral. The integral of 2 over u times du. Since 2 is constant, we can move 2 out of the integral. 2 times the integral of 1 over u times du. Then integrate to get 2 times ln times the absolute value of u plus c. Then substitute sine x to u. 2 times ln times the absolute value of sine x plus c.
For number 16, we need to find the definite integral of 8 secant x dx. And as you can see, we have here the expanded version of 8 secant x dx. And maybe you're wondering, why is 8 out of the integral? Well, since 8 is constant with respect to x, we need to move it out or set it aside off the integral. What we need to do first is we need to find the integral of secant x for us to be able to find the integral of 8 secant x dx. And as you can see in the example, we already have the value of u, which is secant x plus tangent x. And by substituting the value of u to ln, the absolute value of u plus c, we can now get the integral of secant x, which is ln the absolute value of secant x plus tangent x plus c. And obviously, we're not yet done because what we're trying to find is the integral of 8 secant x dx. And by adding 8 to the integral of secant x, we now have our final answer, which is 8 ln the absolute value of secant x plus tangent x plus c. Number 17. Find the definite integral of 2 cosecant x dx. And as you can see, we have here the expanded version of 2 cosecant x dx. And maybe you're wondering, why is 2 outside of the integral? Well, since 2 is constant with respect to x, we need to move it out of the integral. So, the first thing we need to do here is we need to find the integral of cosecant x for us to be able to find the integral of 2 cosecant x dx. And as you can see in the example, we already have the value of u, which is cosecant x minus cotangent x. And by substituting the value of u to ln the absolute value of u plus c, we can now get the integral of cosecant x, which is ln the absolute value of cosecant x minus cotangent x plus c. And obviously, we're not yet done because what we're trying to find here is the integral of 2 cosecant x dx. And by adding 2 to the integral of cosecant x, we now have our final answer, which is 2 ln the absolute value of cosecant x minus cotangent x plus c. For number 18, we need to find the definite integral of dx over 25 square root of 1 minus x squared over 25. And what we need to do is we need to substitute the equation to the formula. And the formula we're going to use is the integral of dx over the square root of a minus x squared is equal to 1 over a arc sine x over a plus c. And after doing that, we now have our final answer, which is 1 over 5 arc sine x over 5 plus c.
Number 19. Let's say we need to integrate dx over 9 plus x squared. The first thing we need to do is to substitute the equation to the formula, which is the integral of dx over a squared plus x squared equals 1 over a arctan x over a plus c. Then, dx plus 9 plus x squared will be equals to 1 over 3 arctan x over 3 plus c. Number 20. Let's say we were given the task to integrate dx over square root of x squared minus 9. First thing we need to do is to substitute the equation to the formula, which is the integral of dx over x square root of x squared minus a squared equals 1 over a arc sec x over a plus c. Then our final answer will be 1 over 3 arc sec x over 3 plus c.
So that's it for our presentation. Hopefully you like our video. Again, that is all. Thank you and see you next week.